All right, so let's look closer at the crystal field splitting. So let's specifically talk about how the electrons feel in these d orbitals, right? So we're still talking about octahedral complexes, right? This is how the orbitals split energetically. And now we want to talk about how will the electrons feel in and occupy these orbitals. So they'll follow off-bow principle, where the orbitals, they're filled in such a way to give the lowest total energy, right? So that means that they're going to singly fill in the orbitals first before pairing, right? Because that'll result in a lower energy. So the energy, when we start to have two electrons in the same orbital, right? We describe the energy needed to be able to pair up two electrons as the pairing energy. So essentially, when we think about how how the electrons are going to feel in these d orbitals, we're comparing the magnitude of the pairing energy, right? The energy needed to place two electrons in the same orbital to the octahedral splitting, this difference in this energetic levels here. To determine, are we going to put, one electron in each of these and then go here, or are we going to put one in each of these and then pair them first before jumping to the higher energetic level? And the way we determine that is by comparing the pairing energy and the octahedral splitting energy difference. So let's look at an example for a metal before it's complex with the ligand. So if we don't have a ligand being bound, all 5 of these orbitals are degenerate, which means equal in level, right? All 5 of them are equal in level. So let me just go back really quick. In this splitting, right, these 2 orbitals are degenerate, they are equal in level, and then these 3 are equal in level, right? But when we don't have a ligand, all 5 are equal in level. So the electrons will feel these orbitals according to Hund's rule, right, which says that each electron will occupy each orbital singly before pairing up. So if we look at an example with iron 2 plus, which has 6 electrons, non-bonding electrons, this is how it's going to feel in these orbitals, right? It's going to fill in 1, 2, 3, 4, 5. Then it's going to pair, right? Then it's going to pair. Now let's look at if iron is complex with the ligand. And we're going to compare 2 ligands along our spectrochemical series. So we're comparing water complex with water versus cyanide, right? So let's look at cyanide first. So when iron is complex with cyanide, right, we have these 6 non-bonding electrons, and the splitting is as shown here, right? Cyanide is a strong field ligand. So because it's a strong field ligand, we're going to see a larger crystal field splitting here. So when we think about how these electrons fill in these orbitals, because the crystal field splitting is so large, they're going to fill it in one by one according to Hund's rule, and then they're going to pair because the pairing energy is much less than the crystal field splitting energy. So it'll take less energy to just pair up with these versus putting one in each orbital and then having to overcome this, like make this huge energetic jump. So for a strong field ligand, the electrons are going to pair in this lower T2G orbitals first before going to the EG orbitals. This is what's called a low spin complex. And it's called a low spin complex because the electrons fill the orbitals in such a way where the number of orbitals with a single spin or a single electron is minimized. So it's called low spin. Now, if we look at iron complexed with water ligands, right? And if we compare water to cyanide, it's a lower, right, or a weaker field strength ligand. So this crystal field splitting is lower, it's smaller. So the electrons are going to fill in these orbitals where it's going to go one here, one here, one here, and then it's going to jump to the E sub G orbitals unpaired before pairing in an orbital. So in a weaker field ligand, it turns out that the pairing energy is higher than the crystal field splitting energy. So the electrons are going to singly fill in every single d orbital of the T2G orbitals and E sub G orbitals before pairing. And because we have a higher number of orbitals with one electron or a single spin, this is called a high spin because the number of orbitals with a single electron is maximized. So this is called a high spin complex. High spin complex. All right, so let's just summarize what we just looked at. Crystal field splitting specifically for the octahedral geometry, right? If we have no ligands, all those d orbitals are degenerate. Electrons fill in according to Hund's rules. Hund's rule. If we have a weaker field ligand, we're going to have a smaller crystal field splitting, and the electrons are going to fill in all of the T sub 2G and E sub G orbitals before pairing. It's called a high spin complex. And if we have a strong field ligand, this crystal field splitting is much higher. So the electrons are going to feel the T sub 2G orbitals. It's actually going to pair with them first before going to these higher energy orbitals. And this is called a low spin complex.